So my name is Mitchell Hernandez. I'm a senior at Colby College in Waterville, Maine. And this summer I was studying active galactic nuclei in the millimeter and gamma wavelengths. And I did this using data from SPT and FAVA. So I'll start with an introduction. So an active galactic nuclei is the term which we use to describe a black hole at the center of an active galaxy. AGN can be different from other black holes in that they emit a jet of material which runs perpendicular to their accretion disk, like you can see right here. And so when a nuclei is emitting this jet, it's called a quasar or a quasi-stellar object because the light from the jet will actually be so bright that it blocks out the rest of the light from the galaxy. So in this image down here, you can see a jet which is pointed towards Earth. And then when you use a coronagraph to filter out that light, you can see the galaxy in the background. And then somewhere in here would be the black hole. So when these jets are pointed directly towards Earth, they're called blazars or blazing quasi-stellar objects. And so this means that the angle that you're viewing the jet from will actually determine what you call the nucleus. So this is a cool chart to show you different angles and what you would call when you're looking at a quasar from different angles. And so up here, blazars when it's pointed towards Earth, and that's what I was looking at this summer. So some physics behind the AGN. So there's a large blob of gas that falls into the black hole, but some of the gas will actually miss, and it will be deflected out of the jet. And so in these disks, there's a bulk flow of very hot and fast gas, which is created. And then this gas is radiated away from the disk into the jet in a very complicated magnetic field, which you can see in this top right image. As it moves away from the disk, the gas starts to expand and cool. And as it cools, the electrons in the gas also start to cool, and some of their energy gets radiated away. At the same time, other electrons will start to speed up in the magnetic field in a process known as Fermi acceleration. So the AGN can vary in their light output due to the turbulence in the disk. And so when a large blob of material falls into the black hole, then it would lead to an increase in gas being ejected from this jet, and it could appear brighter. So my research this summer focused on the 20 brightest sources that the South Pole Telescope could observe in its field of view. So the South Pole Telescope takes data in the millimeter wavelength light, and I use that along with the Fermi Gamma Ray Detector, which takes data in high and low energy gamma rays. And so then this data is made available to the public through FAVA, or the Fermi All-Sky Variability Analysis. And I used a combination of SPT and FAVA data to study the acceleration of particles inside of these blazar jets. So this top image up here is of the South Pole Telescope, and it was taken this summer, and it's a cool image. You can see the southern lights as well as sunset in the background. And then the image right below it is of the Fermi Gamma Ray Detector. And this is currently orbiting the planet, and it counts individual photons of high and low energy gamma rays. So most of what I was doing this summer was making light curves. And this is an example of one light curve for brightness versus time. And this is from the blazar PMNJ0210-5101. And this is what we call the focus quasar because it's the brightest quasar in our field of view, and it's used to calibrate and focus the telescope. So in this graph, data was collected from 2018 up until 2020, and you can use this key in the top left of the image. And you could see that I plotted the three different frequencies, 90, 150, and 220 gigahertz for South Pole Telescope data, as well as the high and low energy gamma ray data from FAVA. So it is important to note that the Fermi data down here, the little plus signs, were actually scaled relative to the SPT data. So I wasn't looking at the actual flux values as much as I was looking at the peak and trough relations along this x-axis, so sort of when they happened in time. It's also important to note that there are these large gaps in the SPT data from when the sun comes through our field of view, and then we can no longer observe during those times. So sometimes the gaps are sort of unfortunate, like when it looks like we missed a peak right here. But generally, we're able to get a full range of data. And so this is the first time that anyone has really looked at this millimeter data over this long of a time frame. And it's also the first time anyone has compared SPT and Fermi data. So this was pretty exciting. So I wanted to point out some interesting points in this light curve. So right here, around 58,650, which happened in 2019, the SPT data for all three frequencies seems to have peaked. And these frequencies seem to have gotten very close together in flux up here. But then you look at the 2020 data, and it looks like this 220 band is significantly lower than the 90 and 150. So that kind of changes over time. And then there's also this lag. So if this is a peak right here, around 7 days later, there's a peak in SPT data, and this lag time will actually change between 1 and 7 days throughout the data. So I made some plots from different interesting points in the graph. So the two plots on the left are from this 2019 peak, and I plotted the 220 gigahertz data over the 90 gigahertz, and then the 150 versus 220 below. And I did this for the 2019 peak on the left, and then this 2020 data on the right. So I did this because the slope of this graph can be used in this equation right here. So in this equation, alpha is the spectral index of the source at that time. Flux 1 over flux 2 is the slope of the plot, and then the frequency 1 over frequency 2 would be 220 gigahertz divided by the lower frequency, either 90 or 150, depending on which plot I was looking at. So using this equation, I was able to determine spectral values for the 2019 and 2020 data. So for 2019, I got negative 0.1 and negative 0.045 for 50, or for the 150 and 90 gigahertz data. And then this changed to negative 0.2 and negative 0.07 for 220. So these changing indices suggest that the temperature and energy of the electrons is changing very suddenly. So when the numbers get less negative, it's called a hardening of the indices, and this suggests that there's an increase in the amount of high energy electrons. So this increase could be due to some sort of injection of energy into the gas, but we still don't exactly know why there would be such an injection of energy. But based on the hardening that I saw, because these numbers are less negative than the ones for 2020, there seemed to be an injection of energy at this 2019 peak based on that hardening. So along with that, we have this lag, which happens when, you can see right here, if this is a peak for FAVA, and this is a peak for SPT, these two would probably correlate with one another. And so this is a 7-day difference, and this is a 5-day difference for the peaks versus the troughs. So you can see the lag does change throughout the plot, and it changes over time very frequently. So this delay could be in part due to a process called synchrotron self-absorption. So synchrotron emission is where light is radiated away from electrons as they change direction inside of a magnetic field. And self-absorption is sort of the opposite of this, when light is actually absorbed by the gas inside of this jet. So absorption usually occurs at higher wavelengths, but then as the gas starts to expand and cool, it starts to brighten again at these longer wavelengths since there's less time. And so this can cause millimeter light emission as well as other emission to appear to have a slight delay relative to this gamma ray emission. And the SPT is always behind the Fermi data. So this relative flux data shows there's this large peak in flux right here for SPT, and it correlates to this very small peak for FAVA. And you can see these two over here for 2020 data are a lot closer. So this difference in intensity for this 2019 peak could be due to the source of gas, which is being absorbed by the black hole at the point in time. One theory is that the high energy injection event, when gas fell into the event horizon, could have led to a gamma ray opacity, where this high energy gamma ray light was absorbed by electron-positron pair production inside the gas of the jet. And this could explain the lack of a peak in gamma wavelength light, but a very strong peak in millimeter. And then along with that, there's another explanation that says the gas is actually cooling and the peak emission is just moving from gamma to millimeter, in which case this dip in luminosity from baseline would just be a coincidence. So future research in this field. So my research focused primarily on millimeter and gamma wavelength light. In the future, I could look at these AGN or others in a wider range of wavelengths, such as X-ray or radio. And this could help to find similarities in the data that I've already analyzed from SPT. So I could look for bigger or smaller lags between these wavelengths, as well as a correlation in brightness of a source across the EM spectrum. And then I could also look at these AGN over longer periods of time. So I could look for patterns if I looked over multiple years worth of data. And I could also look for fluctuations like what I found in some of these light curves for data that was just prior to 2018, when this generation of the telescope was, or I guess, put online. And then I didn't think too much about this yet, but I could also look at polarization data from SPT as well as other detectors, and this could give me a better understanding of what's happening in these sources. So I have these images down here, which I thought were cool. This is in millimeter, X-ray, and gamma wavelengths. And this is a side view of the Milky Way galaxy. And what was interesting were these bubbles right here, which could either be the remains of an AGN from when our galaxy was in an active galactic nuclei phase, and these jets could have sort of expanded over time, or they could also be Fermi bubbles from a supernova that had exploded at one point and sent gas in these sort of bubbles coming on either side of the Milky Way. And so finally, I just wanted to thank some people who I worked with this summer. My mentor, Dr. Nathan Whitehorn from Michigan State University, as well as Alan Foster, John Hood, Kyle Ferguson, and Sam Guns, all of whom helped me get some of my data and make some of my plots this summer. And I could take any questions.
Thanks. This is really interesting. And I'm just curious, you're seeing spectral index changes in the radio. And are you seeing any spectral index changes in the gamma ray as well? Because one would imagine it could be, it's often coming from the same electron population. And, you know, if you're getting synchrotron self-Compton, you might see a reflection of that in the gamma rays.
Yeah, so what I did for the spectral analysis, I didn't do too much spectral analysis. I was mostly focusing on the light curves. But the easiest to do was just from this millimeter data. So we hadn't done the gamma ray data yet, but that would be interesting to look at the different spectral indices at different wavelengths also. And that's something I could continue if I use radio or X-ray data in the future.
Mitchell, nice talk. I had a question that was very similar to Tim's. I was wondering if the other gamma ray band, which is, I think, the purple crosses, does that give you any sort of separate information about lags, time lags relative to the first gamma ray band or the SPT data?
Yeah, so in general, I'm only showing one light curve here, but in general, when there was a peak in the low energy gamma rays, there was also a peak in the high energy. And so there weren't that, so it's by individual counts, individual photon counts, that I got these this data. And so I had to kind of change the scale and change how I plotted it. But in general, when there was a peak in the high energy, there was also a peak in the low energy for gamma rays. So they pretty much stayed together. But it was interesting because there was a lag between the lower energy and the high energy data. So there wasn't as much of a lag between the gamma rays, but there was between gamma rays and millimeter.
Cool, thank you.